Now let's have a look at using the actual three-phase volt drop tables and the application of using the VC formula. So you can look. These tables are three-phase volt drop tables. So we have to convert, do a conversion if we're going to apply it to a single-phase circuit. Now, in this case here, I'm going to use the VC formula to take to the table and determine the size cable that I require to suit the volt drop requirements here. Now, in the formula we have 1000 VD. Now, that VD is the actual volt drop that's permissible. Now, that volt drop can vary as a designer. You'll apply a certain percentage, a certain part of that 5% that's allowed. So a total of 5% volt drop, but you're not going to put that. You're not going to allow the 5% volt drop for say a consumer's mains or a final sub-circuit. You'll apply a portion of that. Now that may be maybe 3%, as we're showing here. Say in this case of a three-phase circuit. Or where it may be 12 volts, or 2% where it may be 8 volts. So we'll apply that portion of the volt drop that's permissible into the formula. So if we've determined we've got say 2% for our consumer's mains, then we'll use the value of 8 volts, which is 2% of the 400 volts, in the formula. We'll use the root length of the circuit and the maximum demand that we've calculated for the circuit, which will then give us the VC value. We take that to the table. Because this is a three-phase circuit, it's a three-phase table, there's no other conversion required. We take it straight to the table. Now, the VC we look up must be lower than the calculation that we've done for the VC. So it's an opposite approach when we do to current carrying capacity when we're looking into the tables. So we find a value that is lower than our calculated value. Cross-reference that to determine the size of the cable that's suitable for that volt drop requirement. Now, in this case, I'm going to use the VC to determine the actual volt drop I'm going to occur when my cable has the full load current flowing through it. So again, I've got a three-phase circuit, so I'm going to go into my three-phase table. Here I'll be looking up. This will be for a given size cable. Whether that cable is 4 mil, 6 mil, or so forth. I'll look up the VC and put that into the formula. So my VC will go into the formula, and that will provide me with an actual volt drop, that will occur, like I said, when that full load current is flowing in that conductor. Now, in this case, I've got a single phase circuit. So this is the process of using the three-phase tables with a single phase circuit. So in this case, I'm going to use the VC to determine the size cable that's suitable to meet the volt drop requirements. So again, I'll be for the value of VD, I have to determine how much of that percentage, that 5%, I'm going to apply. So for whatever I'm permitted, whatever voltage drop I'm permitted there. In the case of a single phase circuit, it's up to 11.5 volts of the 230 volts. So if it's 3%, I'll be using 6.9. If it's 2%, 4.6 volts, or any percentage in between that's deemed to be suitable for that. So I apply that the VC, 1000 times the VD, times divided by the length, times the maximum demand or the current rating. Now, once I've determined that VC, I have to multiply it by 0.866 to take it then to my three-phase table. Okay, so I've got to convert it to a three-phase value. So converting my single phase. Now remember, this is a VC, so it's not a voltage. It is a millivolt per ammeter. So the conversion factor from single phase to three phase is 0.866. In this example, I'm looking at determining the volt drop that's going to occur in a single phase conductor, whether it's a consumer's mains or a final sub-circuit. Again, the VC that I'm going to use is going to be determined by the cable size. So I'll cross-reference the cable size in the table, VC table, and that will give me my actual VC. Now, to use that VC from a three-phase table into my single phase calculation, I have to multiply it by 1.155. So my three phase table going into for the calculation for my single phase circuit to determine the actual volt drop, I'll multiply by 1.155. Now, in this example, I'm using a three-phase consumer's mains. Which is V75, 4 V75 SDI cables, so single core double insulated cables and earth, and it's been sized. The active's been sized at 35 mil to suit 120 amp maximum demand. Okay. Now the circuit route is 80 meters, so now I have to say, is the cable 35 mil cable large enough if the volt drop is not to exceed 2.5%. So as a designer, I've applied this 2.5% for the consumer's mains. So I now have to determine if this cable is large enough. So 2.5% of the 400 volts is 10 volts. So my VD here will be 10 volts. So applying that to my calculation, I've got 1000 times 10, which is the VD. I've got a length of 80 meters and a current of 120 amps. This gives me a VC of 1.04 millivolts per amp meter. Now here I'm going to be using my three-phase volt drop table, table 41, for my single core cables, my single core double insulated cables in a wiring enclosure. Now it is V75, so I'm using a table operating temperature of 75 degrees, so I use that appropriate column. I then look down with my 1.04 millivolts per amp meter, and I find a value that is less than my 1.04. So in this case, I'm having to upgrade my cable to a 50 millimeter cable to suit the volt drop requirement for that route length of 80 meters.